order to make concepts even more clear about the Thevenin and Norton equivalent, let's just solve this new example. You can instantly see that there is a dependent source involved, so you cannot use a simple method of finding R Thevenin. You would have to find VOC as well as ISC. So let's just start off by finding VOC. By the way, this Vx, it is the voltage across this resistance. So let's just start off by finding VOC. For that, you just need to open this terminal over here. So I just opened the terminal and I marked this voltage as VOC, and you need to remember that this is also Vx as shown in the previous depiction. So now we need to find this VOC. So let's just apply the mesh analysis. There are two meshes, I1 and I2, and clearly there's a current source, so there would be a super mesh. So KVL on SM12. Also I2 is 0, so this is something you need to know. So let's just apply the KVL. So -4 plus 2000 I1, and I move here. So there is plus 3000 I2, which is 0, plus VOC is equal to 0. So this is 0, so this will just disappear. And then also another equation, because there's a current source here. So that is minus I1, I2 minus I1. This is equal to VOC divided by 4000, and I2 is 0. So that means I1 is equal to minus VOC divided by 4000. So I have two equations and I have two unknowns. So I can just plug them in and find the values. So by solving the two simultaneous equations, this is what I got for VOC. So this is our VOC. Now let's find ISC, and for that I would need to short this terminal here. So let's just do that. So now I shorted the two desired terminals, and now let's find the current through those two terminals, which is ISC, the short circuit current. So Vx over 4000, this is Vx. Now clearly you can see that Vx is equal to 0 because there is no element connected. So the potential difference between these 2 points, that would be 0. So you can just remove this current source because there's no value of it. So if you remove a current source, it becomes an open circuit. So the circuit you would get is this. So after removing the current source, you will just get a simpler circuit. So now let's apply a KVL or whatever to find the current flowing here, which is the same, and ISC. So ISC would be 4 divided by the total resistance, which is 5000 ohms, and that would be 0.8 milliamps. So now I have VOC, which is 8 volt, and I have ISC, which is 0.8 milliamps. So to find R Thevenin, I can just use this formula, and I will get 8 divided by 0.8 milliamps, and that would be 10 kilo ohms. So this is how you can find a Thevenin equivalent if there are dependent sources involved. But wait, what if there are only dependent sources involved and there are no independent sources? So this is our last case scenario where we have no independent sources in a circuit. So if there are no independent sources in a circuit, that means VThevenin would be 0 volts because there is no voltage, and I Norton would also be 0 amps. So let's just see this through an example. So imagine you have this circuit and you need to find the Thevenin equivalent. One thing to clearly observe is that there are no independent sources here. So there would be no current or voltage through this circuit. So the Thevenin equivalent would look something like this. Just a resistor in parallel with our Thevenin in parallel with our resistor. So, but how do you find R Thevenin? You can clearly not use the VOC or ISC method because there is no voltage or current involved. So what to do when you get a circuit like this? It's very simple. Use a test source. The concept behind the test source is that you just replace the your terminals, the desired terminals, with a small 1 volt voltage source or whatever value. I'll just use 1 volt. So I'll just redraw the circuit. So I can just replace my resistor, and between the two terminals that I need the VOC and ISC, I'll just connect a small source. It can be a current source and it can be also a voltage source. So in this case, I will just use a current source, for example, a 1 amp current source. So now I just need to find the voltage across these 2 points, and that would be my VOC, like my VOC. So let's just see this through, and let's just solve the circuit. So I'll just apply the mesh analysis, and I1 would be 1.5. I'll just call this IX, to not confuse the numbers. So I1 would be 1.5 IX, and I2 would be, because this I2 is this current, I2 would be equal to minus 1 amp, and Ix, because Ix is clearly in the direction of I2, so Ix would be I2, and that would be 1 ohm, 1 amp. So I1 would be 1.5 amps. So these are the currents that I get. So now to find this given voltage, let's just apply KVL. So we'll just use this loop, just go from here to here. So the voltage across the 2 ohm resistor, that would be I2 minus I1, and then plus VOC is equal to 0. So that would mean 1 minus 1.5 plus VOC is equal to 0, and VOC is equal to 1 volt. So this is the voltage I get. So now to find R Thevenin, what I can do is I can just divide this voltage by the test source I used, 1 amp. So my R Thevenin would be 1 ohms. So this is how you can solve circuits when there are no independent sources involved. This method would also work if I had used a 1 volt test source here. I'll just show that too. So if I have a 1 volt source, I need to find the current flowing through it, and I'll just call it ISC. So before I had a current source, I had a current test source here instead of the voltage source, and I used the voltage across it. But now I'll just do the opposite, and I'll use a voltage source, and I'll show that it makes no difference. So let's just apply the mesh analysis. So this is IX, by the way. So by applying mesh analysis, I can apply the because there's a current source here. So I1 would be 1.5 Ix, and if I apply the KVL on mesh 2, so that would be 2 I2 minus I1 plus 1 is equal to 0, and I1 is clearly 1.5 Ix, so that means 2 I2 minus 1.5 Ix equal to minus 1. I have just one equation and two unknowns, but I know that I2 is equal to Ix2, so I can just substitute that. By substituting I2 is equal to Ix, I get this equation, and if I solve this for Ix, I would actually get an answer of 0. I'm sorry, Ix would be 1 amp. So ISC is in the opposite direction of Ix, so ISC would be minus 1 amp, but it makes no difference if it's a negative or a positive current because it's just assumed to be going out. So R Thevenin would be just the absolute, the positive of VOC divided by ISC. In this case, VOC is the test source, 1 divided by 1, and that means 1 ohms. So this is how you can use any test source, a voltage source or a current source, in the terminals you desire to find R Thevenin. This method would only be used if there are no independent sources of a circuit. So I'll just summarize everything we have learned about Thevenin and Norton until now. Or so this is the summary. If we have a normal circuit that has no dependent source and only independent sources, we can find VOC by opening the terminals. If there's a dependent sources, we can find VOC by the same method. But if there are no circuits, independent sources, finding VOC is not applicable. ISC can be found using the short circuit and normal circuit. With the dependent sources, it can also be found with the same method, but with no source involved, it is not applicable. There won't be an ISC. For the R Thevenin in a normal circuit with only independent sources and no dependent source, we can use both methods that we have studied. One with VOC and ISC, and one where I just remove all the sources. But if there are dependent sources involved, to find R Thevenin, I can only use VOC divided by ISC. And if there is no independent source, I would have to use the test source method that I just described in this video. So these are the methods to find the Thevenin or the Norton equivalent of a circuit, and we've already seen how they are really helpful in analyzing circuit's effect on a single component. So I hope that these examples have made things even more clear.